we'll go ahead and get started. I know there are still some folks coming in, and I'll continue to let them in. But at first, I wanted to thank our speaker, Mr. Dennis Bushnell from NASA Langley, for coming to talk to us. And just a brief introduction by Mr. Bushnell. Dennis Bushnell is currently the Chief Scientist at NASA Langley Research Center. He is a member of the National Academy of Engineering, an honorary AIAA Fellow, and ASME and Royal Astronautical Society Fellow. And over the course of his career, he has given over 500 invited lectures and has 270 publications. And the history of his professional pursuits includes working on the Gemini, Apollo space shuttle programs, the X-15 program, submarines, torpedoes, rockets, viscous drag reduction and flow control, CFD, revolutionary transport configurations, SST, personal air vehicles, and commercial deep space, future warfare, frontier power, and energy and climate. So he's going to talk to us about the frontiers of responsibly imaginable.
All right. Yeah. This is about big ideas for barrier problems. Next chart. Next chart, please. The first barrier problem is the fact that, particularly in space, everything we try to do, the costs of it are dictated by chemical energetics. So let's look at beyond chemical. You're familiar with nuclear fission, thermoelectric. It turns out, compared to the next one here, it's very heavy, but it's 10 to the 7th times chemical because it's about 8-9% mass energy conversion. At NASA Langley, Sang Choi has invented a new nuclear battery that produces 22 kilowatts per kilogram of isotope. The current RTGs that we've been using for many years at great expense, the plutonium-238, produce 10 to 15 watts per kilogram of isotope. This is 22 kilowatts per kilogram. This new nuclear battery has an alpha, a total kilogram weight per kilowatt produced, of order 1. Reactors have an alpha of anywhere from 35 to 100. So this is 35 to 100 less weight than a reactor. And it's less expensive, it's safer, and this will allow powering essentially everything in space. It scales from milliwatts to tens of megawatts very nicely, can power propulsion spacecraft, ISRU, on-body HABs and transportation, and it can power Vasimir, which is an MHD rocket that's now been shown to have 6,000 seconds of ISP instead of hydrogen oxygen chemical, which is 453.35. Beyond this nuke battery is positrons. These are anti-electrons. It's the cheap antimatter. When you have a PET scan, those are positrons. We can store it now. And when it's annihilated with electrons, it produces 100% mass energy conversion, not 8% like fission. So it's 10 to the 9th times chemical, produces half an MeV gamma that we can thermalize. Next chart, please. The intact physics, how Sang Choi pulled this off, it turns out that most other nuclear batteries use very low energy isotopes, so they break loose the valence electrons, and there's only a couple of those. What we do is use very energetic isotopes like sodium-22, cobalt-60, or cesium-137 to break loose the intraband electrons, the inner electrons, and there's a whole lot more of those, like 10 to the 4th, 10 to the 5th more. So that's where the energy comes from. And it can be used, it can be used beyond space. It turns out that you can put nuclear waste into NTAC and it will produce massive amounts of energy. It can eat nuclear waste for breakfast. So nuclear waste contains 85% of the energy still, and is becoming a very great problem, including for terrorism. So this will so DOE is very interested in this. The National Security Space is interested to power that with this. Ships, submarines will work, and we're working with someone from South Africa who has a mile, 2.5 mile deep a gold mine who's wants to use it to power that. Next chart, please. Okay, now we're going to transports. Okay, what about long range transports? People now want to use safe fuels, which are biofuels or hydrogen, for wholly emissionless because it pays for the CO2 up front. Well, that's not really true. They're not emissionless because if they use these safe fuels and fuel cells or burn it, they produce water. And with hydrogen, you produce a lot of water. And therefore, and water is, about twice as bad as CO2. It's the worst greenhouse gas because there's so much of it. Plus, you mess with the ozone because you produce NOx. So the only real emissionless aircraft is batteries. And the key to doubling the range of a given battery energy density is for us aero people to do our job and to double L over D, and that'll double range, and I'll get into that. In terms of batteries, we now have lithium-ion batteries, 250 watt-hours per kilogram. Lithium metal are coming online now at 500 watt-hours per kilogram twice. And then lithium air batteries are about the best we're going to have. Argonne and other people are producing those or developing them, and they're 6 to 8 times lithium ion. So in terms of range for electric batteries, the lithium ion, you can get about 400-mile range with a good L over D on a transport configuration. Not these AAM things with all of these rotors beating the air into submission and producing drag, but a good cruise configuration will get about 400 miles. The lithium metal batteries at twice that will get about 800 miles. The lithium air batteries at 8 times would get 3,200 miles. And now if we aero people do our job, we can double that to 6,400 miles, totally battery electric going forward. It's up to us. Next chart, please. Now, how do we get to drag reduction? Okay, you've heard of truss brace wings. I gave Boeing the truss brace wings at a Green Aero meeting at Ames around 06, and they used it for the next gen, third generation efforts with their Boeing Sugar configuration. We've worked with them on truss brace wings ever since. They took what I gave them and they used the vanilla version. So what we're getting with truss brace wings is about 20% L over D increase. What I'm going to give you here is more like the full monitor, the full configuration change that I gave Boeing. Okay, so we're going to increase span to reduce drag to the lift. So we're going to need hinges for the 80-meter airport gates on the wings, and Boeing's got them. We're going to double span nominally and have the cord to get the same lifting area. We're going to reduce drag due to lift, therefore, which is 40% of the cruise drag, by 75%. And we can reduce wing weight in some studies up to 40%. And then the truss allows us to thin the wing down and unsweep it. And therefore, without going to the agony of suction, we can have about 60 to 70% of wing areas natural laminar flow. So therefore, that'll reduce the skin friction by about 60, 70% on the wing. Then you move the engines to the rear of the fuselage. and you ingest the fuselage bottle air to get that 10%. And then you take the engines and you thrust vector them for control like the military does. And you get rid of the empennage, no tail, drag, and weight. And a former student of mine up at Notre Dame has invented a plasma turbulent drag reduction approach, which he's now flying. He's proven it out in the wind tunnel. It produces 60% net turbulent drag reduction. So we can use that on the fuselage and the rest of the wing. The L over D from all of this, from work we funded at VPI and from Feniger's work on something similar, is in the 40s to 100 instead of the current 18 to 22, which will easily double range for a given battery energy density. Next chart, please. Okay, the AAM vehicles, as I said, are beating the air into submission with all these rotors. Their range is not good. We've got to get better configurations. The best I've seen is the stopped rotor design created in the 50s. This is a large two-bladed rotor. The rotor is turned with tip fans to reduce the drag to the lift. And if you turn the blade this way, you don't need a tail rotor. At altitude, when you're ready to cruise, the rotor stops, becomes the wing. The tip fans become part of the propulsion system to reduce drag to the lift. And the problem has been when you stop the rotor, one of the blades is turned the wrong way. And now we have morphing these many years later to reverse the sense of the airfoil. This thing has very low cruise drag, very low energy use. It's very efficient for VTOL and very low noise for VTOL. Next chart, please. Okay, we're about to increase the number of aircraft as we get the market build up for AAM and personal air vehicles from 36,000 aircraft, worldwide now, to something like tens of millions, 36 million and far more. And the current ATC system is not scalable to that level of traffic at all in any way. And the current one has to always work. And it has huge human operational latency. And I've interacted with the FAA on their next gen and what they've been trying to do over a couple of decades now to make relatively minor modifications to the existing air traffic system. It's taken a very, very long time. When they showed me what they were doing, I asked them a simple question. I said, okay, once you finish this sometime around 27, 28, how many UAS in controlled airspace can you allow? And they said 7,000. And I said, well, we need, tens of millions. So that's where that ended. The approach that I think we could take to get the air traffic control system we need to not impede the market buildup of what is a new $1.5 trillion per year AAM paved market worldwide is to wrap a giant simulation around the current air traffic system, extract data from it, but don't interact with it, let it run. Develop in this sim the various piece parts and system of systems. You can do it fast because you don't have to worry about impeding the current one. All the nav sensors, comms, controls, computers, collision avoidance, all of that. I've got all that documented in a TM if you want to go look at it. And then take it down and physically demonstrate it down in the desert, validate it. And when you're happy with it, reach inside of it, turn off the existing ATC system, and the sim becomes the ATC system. Next chart. We can do that in 5 years. All right, where are we going to get the electrics for all these electric aircraft? Green electric. We're going to get it from renewable energy, solar, wind, geothermal, biomass, hydro, and storage. And the storage costs have been plummeting, as have the renewable energy costs, and that's why the costs are now less than fossil carbon and nuke. And so we're closing nuke plants, coal's going away, and gas is starting to drop. The wind and solar cost is less than 2 cents a kilowatt hour. Solar is now dropping below 1 cent a kilowatt hour, and all of this is still dropping. We have now figured out how to make solar twice as efficient because we can now produce 2 electrons per photon instead of one. That'll almost double the efficiency. So people are starting to talk with me about energy too cheap to meter. Worldwide, renewables now generate 29% of all electricity, and that's growing rapidly, that percentage. And for many years now, they've been over 90% of new generation because they're so cheap. There's major investments in storage. Storage has dropped in cost by 70% in the last 3 years. There's a lot of money in storage research because the market is so huge. People are now putting out into the grid storage iron air batteries, which are half the cost. All of this green energy, cheap storage, will enable distributed energy generation, putting the solar on your roof with some storage, so you don't have to pay for the increased costs of the smart grid and all the rest of it. You can do mineral extraction from the seawater with this cheap energy instead of mining. Mining's the worst thing we do to the ecosystem. And we kill 8 million people a year due to the pollution from all of this fossil carbon fuels. And so we can save those lives. Next chart, please. So bottom line, green energy is going to be here for electric transportation. Thank you. Next chart. Revolutionary materials. Well, when we make materials, we process them in up to 17 ways. And in the process, we produce grain boundary problems and dislocations and end up losing up to a factor of 20 in material properties. The MIT people, Professor Shu, and others are now printing at the nanoscale and producing stable, superb microstructures. They have 5x materials now. So 5x of the 20x, and they think they can get 10x. We can also merge the nanotubes, produce nanotube structural materials instead of nanotube composites, and it gets similar results. And then there are 17 material processing approaches, and every time we've utilized 2 or 3 of those, especially combinatorially, we get different and sometimes better materials. 17 combinatorial possibilities is 17 factorial number of approaches we need to take and look at experimentally in order to find out, do material discovery. Next chart. Okay, this is the electric to electric storage. And this is not good for hydrogen. Hydrogen is half the efficiency of electric to electric energy storage of practically anything else. Hydrogen is also corrosive, so you need new engines. Hydrogen is very expensive, green hydrogen. It's really hard to store. It's volumetrically inefficient, increases aircraft drag and weight, and it produces far more water for climate. So really, hydrogen is probably not the best thing to use. I think that Boeing's done the right thing going to the safe fuels, primarily biofuels. Thank you. Next chart. Okay, for structural nanotubes, we know enough about the chemistry of these things now that we think we can use things like the zipper mechanism of stone whales bond rearrangement, or electron beams or interstitial boron atoms in order to try to put them together to make structural nanotubes. Next chart. Okay, commercial deep space. The major issue with what's developing now, commercial deep space beyond geo, is a closed business case, i.e. how do they make money and profit out there? A major enabler to get the cost down so you can up the possibility of profit is cheap space access. And Musk has really done a beautiful job with this, and other people are now going there. Reusable rockets. NASA looked at them years ago, didn't think they were doable. Must prove they are. The Falcon Heavy is a factor of 6 less cost than SLS, cost to orbit. The Starship is projected as it gets better at $10 a pound to orbit instead of $5,000, and SLS far more than that. And that's going to accelerate all this commercial deep space massively. It turns out fuel is less than 1% of the conventional LEO access cost. The major costs are the hardware and the operations. The operations are a surprisingly large part of those costs. The reusable rockets reduce the hardware costs, obviously. And the developing AI and robotics should pull the human labor out of both the manufacturing and the operations so that we can do even better, perhaps, than the $10 a pound. We'll have to look at that. Then there's the revolutionary materials, which can reduce the cost per pound to orbit and therefore reduce both vehicle weight and payload dry weight and increase the payload weight fraction. Next chart. Space debris is becoming a really serious issue. We're within 1 or 2 collisions of a closeout, because as you have collisions, you make more debris, and this becomes really bad. People are getting really serious about this and worrisome because people are now putting up to 50,000 LEO sats for high-speed internet and other things. And it's really not good. There's a major legal issue why it hasn't been cleaned up. And that's because it's still owned by, whomever put it there. And so you need their permission. We got to fix this. But the real issue that it's still up there is that the fuel, at the cost, particularly the fuel cost to go out and do all this orbit change and all the rest of it, is simply unaffordable. And so nobody's yet signed up to do it. So again, here's Langley with the solution. Next chart. Okay, a spacecraft with an electromagnetic tether operating off of the Earth's magnetic field, powered by either solar or the new nuclear battery. Nuclear battery would be far cheaper. This enables maneuver, capture, and propulsion without using chemical fuels and incurring all their costs and weight. And what we're looking at is, once it's captured, we either add drag with a passive tether so that it'll go down and burn up, or as we collect it, we put it into a space junkyard. We call this cosmic beachcombing, and repurpose and remanufacture it by the piece or the piece part. And we'll look at its station. It's going to go beyond pull date here in a few years. And instead of lowering it, we want to raise it and add it to the junkyard. We can probably reuse an awful lot of that and remanufacture it. Next chart, please. So safety and reliability for on-demand mobility and commercial deep space are really serious issues. One that I think NASA and particularly Langley is going to be working on going forward. As I said, we're heading from 36,000 to 36 million plus of aircraft, and these AAM pay things fly over populated areas much more, and much more operations per day, and they're crashing. One crashed into a lady sitting by a swimming pool in Las Vegas. One started a forest fire. One crashed a helicopter. One flew into the 36th floor window of a building near Wall Street. It turns out to attain the same safety as commercial aircraft for this number of aircraft, these types of aircraft, which are built with cost as a dominant metric, we're going to have to increase their safety by about a factor of 1,000 to get to commercial aircraft safety. And for commercial deep space, since the 50s, rockets have failed about every 100 shots or so. Musk is running about 100 now, and we'll see how much better he does. But over the decades, we've not been able to do much better than 100 shots. I'm in the National Academy. I asked the people that own rockets why it's only 100 shots, and they said because people do dumb things. They put rags in the fuel lines and stuff like that. With commercial deep space, space tourism, we're going to have to do far better than 100 shots. The current 100 shots is again requires a factor of 1,000 better safety to get it to commercial aircraft safety. Next chart, please. The greatest cause of safety issues is in aerospace human factors. It's about 90% of the safety issues is due to the humans in aerospace. The shift to autonomy for UAS and rocket and everything, the rest of it is the fundamental first step. We could get an order of magnitude improvement of the factor of 100 to 1,000 we need. Beyond that, we need to worry about cascading failures. These are failures that are subcritical, that if you look at the individual failure, no, it's okay. But in a system of systems, if several of them cook off, it's not good. And then we need to question everything, exhibit constructive, ubiquitous paranoia, and then use big data collection of all the historical aerospace accidents and near misses, and send in the AI so that we can learn what we really need to worry about. So there's very few unknown unknowns. Next chart. Why autonomous systems? It turns out that autonomous systems can, now or going forward soon, with respect to humans, know far more, be less expensive, exclude this operational human error, have far less latency, new functionalities, far longer duty cycle. The autonomous robotics doesn't have to have coffee breaks, go to the head, eat, sleep, and so forth. They provide new functionalities, have far longer duty cycle, size reductions, faster, more efficient, far more durable, and patient. That's why they're starting to take the jobs. Next chart. GCR is a very serious problem. It's the worst problem for humans in space. It's up to 50 giga electron volts of iron nuclei, fully ionized iron. It's particle radiation. It's not gamma. It's very different from all of the gamma data that we have from the Japanese bombing and all the rest of it. This is different, very different. It's worse. Micro-G decimates Micro-G not only produces carcinogenesis, it turns out it decimates just about every physiological system in the body we now know. So what data do we have for GCR? Effects on humans. We have the Apollo kids out there for a couple of days. That's not very useful. Station, we send people up for nominally 6 months because after 6 months, they've got to get better. It takes them a while. Scott Kelly went up and said for a year, oh no, this is far worse. But up in Van Allen, station is within the Van Allen belts. So it's only 45% GCR, so that's not full GCR. The canonical Mars exploration mission is nearly 3 years, not 6 months or a year. And in space, it's full GCR. And in space is most of the time. Next chart, please. So these are the mitigation approaches, and Langley's come through here again. Biological countermeasures, these are space hardened, genomics to space hardened human physiology. Some good results from that, but that's not the panacea. You can redesign the spacecraft so that all of the piece parts and fluids inside help in a full force by steradians, 360 degrees around, to protect the humans as protection. But the stuff in the spacecraft is higher uh, number, high Z, higher atomic number, and produces neutrons as secondaries, which can be even worse than the GCR. When you're on planets, you're fine. You can ditch and bury or use lava tubes, 3.5 to 4 meters of regolith or ice, and you're okay. We're going to have to go underground. The cartoons you see of these surface habs on Mars, are just not feasible because they cost a lot to bring there, but the main issue is that they provide very little protection for GCR. For in space, you can make a 3.5 to 4 meter polyethylene. You want a lot of hydrogen, low atomic number, overcoat that you can reuse, put in space when you come back and reuse it for the next trip. The problem is that much polyethylene weighs more than the spacecraft. So Langley's come to the rescue. John Newberry, bless his soul, made the observation that for 4 decades in the accelerator community at CERN and others, they have utilized very small curved silicon crystals to redirect up to TeV particle energy. So John says, and John's working now under IRED to see whether we could use this to protect the spacecraft, and then we'll look at possibly protecting spacesuits, which right now have very little GCR protection. So far, it looks like this may work. Then there's fast transits. I've already talked about 200-day round trips, which would obviate the problem with GCR. Using the nuke battery with Casimir, it turns out that Musk is putting up cheap fuel in space with his cheap space access. And with that cheap fuel, he can put the accelerator down and do brute force chemical Mars in 200-day round trips. He can also do, by the way, powered EDL because the fuel is a lot cheaper. And therefore, all this work we've done here on EDL with various parachute-looking things, that may not be necessary. Next chart. Okay, I'm going to give you now a really big idea to finish off here for a really big set of problems. We're running out of reasonable land, arable land. We're running out of fresh water. We're running out of food. We need green energy, and we need to fix climate. It turns out the solution space for this, the best one that scales, that's cheapest, that can solve these problems in 5 years and make profits on the way, comes out of the plant world. Plants are split into glycophytes and halophytes. Glycophytes are freshwater plants. Halophytes are saltwater plants. Halo means salt. Agriculture is freshwater plants, and for them, salt is bad. We are pumping aquifers for the freshwater plants. We've pumped them so much that they're going saline. We're salinating the fields. And we're running out of fresh water. The halophytes, there's 10,000 of these things, produce the same products that glycophytes do, food products and so forth. And most interesting, they grow with deep roots on wastelands and deserts, and they sequester 18% of their CO2 uptake in their deep roots. And with cheap land, cheap water, seawater in deserts, wastelands, we can green the planet, suck up the CO2 out of the atmosphere, and solve climate. 44% of the land is deserts and wastelands. 97% of the water is seawater. Seawater contains 80% of the nutrients to grow plants, so you don't need much fertilizer. And seawater contains trace minerals that the human physiology needs, which are no longer present in our food because we have overused the arable land that we grow the food on. So we take selenium tablets and other things now. Next chart, please. So halophyte characteristics, they have yields equal to glycophytes. They produce seeds, fruits, roots, tubers, grains, berries, rich in energy, protein, and fats. The Chinese have a major production of a halophyte rice. There's halophyte tomatoes, and so forth. The most expensive food item in Europe is a halophyte. Next chart. So the big idea here is to utilize wastelands and deserts to grow food, fodder, and biomass using salt water for saline aquifers, which actually are present under most lands. Most of these deserts and wastelands. There's a huge one under uh, the Sahara, uh, which would, if used, or you pump Mediterranean or Red Sea seawater to do the halophytes in the Sahara. As you do this, the salt water evaporates, produces an unstable atmosphere, produces rain downwind, which means this will put rain back in the Middle East, and we can regrow the cedars of Lebanon. We could, in the near term, then, affordably, with existing tech, in about 5 years, grow all the food anybody wants to eat, release the 70% of the fresh water now used for conventional freshwater agriculture, all that fresh water back to direct human use, utilize the biomass for green energy, for safe fuels, and also for petrochemical feedstock for plastics. Half of the petroleum we now use is used for petrochemical feedstock, and you pull the CO2 out of the air. Next chart. So, as advertised, this solves land, water, food, energy, and climate. India's had a saline ag for food and fodder in its coastal regions for centuries. There's 22 nations that are applying halophytes for food, fodder, and some biomass, and I'm working with a lot of them. Boeing is producing, I worked with Boeing to do this, producing aviation fuel from halophytes grown in the UAE. That's why they like safe fuels. Worked with the plenipotentiary for Aruba in the Netherlands. It turns out the Netherlands solves Aruba. Aruba is a desert island, even though it's a really nice place to go. It's because they've been importing all their water. Now they've got halophytes. And I worked with the tech advisor to the Secretary of State, and we've got a halophyte operation down there, Aswan in Egypt. So this is the last major natural resource exploitation that the humans have, wastelands and seawater. This will buy humanity another few centuries before Malthus kicks in with a vengeance unless we stop growing a population. We're now asking too much of the ecosystem. We're short 50% of a planet now. We go into ecosystem deficit, reducing it still more, crushing it after this month. And as the world tries to obtain Western living standards, there's billions of Asians, and we're going to be short 3 planets as they try to do that. So things are going to get really dicey. Halophyte's the only real serious get well approach at scale with the requisite capacity, which is cheap, which is doable, which is no new technology. Next chart. Okay, last 2 charts. This is the first of the 2. There really is magic in big ideas for tough, important problems. At Langley, for various reasons, over the past couple of decades, we have gone far more to nearer term things and dealing with 0.1x to 1x. Need to go after 10x plus, go where others fear to tread, imaginate. That takes a lot of knowledgeability, but ideate and triage multiple solution spaces for big ideas with massive payoff. Next chart. Last chart. This is from the Leader's Guide to Innovation. When you do this, when you become a tech maverick, these are the people that invent things that the rest of the center essentially lives off of. If it ain't broke, break it. Hire crazies, pursue failure, spread confusion, read odd stuff, consider the unthinkable. I have a tech maverick group, 14 top patent producers, big idea producers at the center, and we meet periodically to try to figure out how to afford to do more of this at the center. Worldwide, we now create wealth by inventing things. In the back in the industrial age, we created wealth by raping natural resources. Now we invent things. The Harvard Business Review says mavericks are the most critical staff going forward. The problem with mavericks is they question everything. They're hard to manage. They're upsetting to many people. The center has not been kind to their mavericks. Whitcomb left early because he was unhappy with the way he was treated. And that happened to the father of one of our current directors. This is the person who invented the technology and developed it for NTF. So, you know, if I can leave you with anything out of this, it's there really is magic in big ideas. The ideas that I've described here are for problems that literally nobody else could solve. Okay. So be courageous and have fun. You know, this is what I do all day and into the night, not weekends, and I absolutely love it. Thank you for listening.
Well, thank you very much for talking to us. We do have a few. Oh, sorry, I keep going back to the wrong side. We do have a few questions. Actually, the first couple are from Carol Wiseman. The first question is about, I think, the radiation faced at the International Space Station. You mentioned, you know, Scott said far worse. What does that mean? What did he struggle with health-wise? Could you kind of explain that?
Yeah. He went up there and he said, you know, spending a year, you know, in that radiation and the microG. Okay, both of them are there, and their concomitant, you know, effects are much more than either one. Although either one has certain special things, and Scott, you know, there's the problems, the health problems go almost through the body. There's problems walking, there's problems hearing, there's problems seeing, there's all kinds of problems. You know, look him up on the web and see what his comments were when he came back. One of the things that, you know, that happened to him was that he got large sores on his skin, you know, from the microG partially. Okay, next question.
Another question, I guess, Carol, if you're online, you're welcome to ask. I'm not quite know how to say your question about the CO2. Do you want to unmute and ask? Let me see if I can. I don't know if Carol, can you hear us? I guess not. I guess she's saying that she is talking. Can anybody else hear Carol? Yeah, I don't think we can hear you. Yeah, I guess you can see her question. It says if I don't know in what context, what slide this was asked, but if CO2 is so bad, why did they pump CO2 into greenhouses and plants convert CO2 to O2? I guess if you, I'm not understanding the context, and maybe if you understand it, Dennis, you're welcome to answer.
No, Carol, can you please send me the question as an email and I'll answer it for you?
Okay.
Oh, it's a general environmental question. Okay, can you put the question in the chat? I'm looking at what you're sending.
Okay. Anybody else have any questions while Carol is crafting her question? Sure, why? Here you go.
This meeting is being recorded.
Yeah. Okay. I guess I will have a. I think she's typing her question. My one quick question, Dennis. You mentioned that you feel like Langley has been going for 0.1x, 1x type of changes versus going for the 10x or multiple x. Could you kind of give an example of what you were considering as something that we're going for 0.1x, 1x, and what we could have done more?
Yeah.
In your opinion.
Sure. How much improvement you're going to produce with your research? Are you going to reduce drag 1%, 5%, 10%? Okay. In other words, go after larger, impacts of your research. The center director now asks all the directors, everybody in the CLC, to send him every other week the impacts of what we do. The center is, regarded favorably or unfavorably, depending upon how much what our impacts are. Much of what we do, quite honestly, doesn't have much impact. And to keep the center, competitive and in business, we need larger impacts. And there's massive problems with the business with the competition, and there's a huge number of societal existential issues, which our research in energy and all kinds of other things can contribute to. Oh, okay. Carol showed me her question, which is, from a growing plant point of view, more CO2 is better. Okay. That's true. But the CO2 is not good from all kinds of other ways. It's warming the atmosphere, and as the ice melts, most of it's in the Antarctic. If all of it melts, the sea level comes up 74 meters, and the shoreline in Virginia is somewhere between Richmond and Charlottesville, and the high rises out in Virginia Beach become hazards to navigation. Okay, there's a huge literature on why CO2 is bad. I'm not going to take the time to go into it.
I think we have another comment from Suresh Joshi, but that's just basically kind of along the line that you mentioned, so it's not really a question. Anybody else have any questions? Otherwise, we can, let's see. Okay, yeah, that's another, I guess, a carbon capture technology discussion from Suresh. Yeah, so Lee Myers has a question. Any recommendation for reading odd stuff?
Every once in a while, I Google the following words: unexplained, anomalous, and so forth, to see what's there. Okay. And odd stuff is For instance, why there's so many unexplained problems in physics. You're familiar with quantum entanglement. Quantum entanglement means that if you entangle things and separate them, if you change one, the other changes instantaneously. The speed of that has been tracked at greater than 10,000 times the speed of light. And no one has an explanation for that. None. How can anything happen at 10,000 times the speed of light? How does the knowledge of you changing something here, alter something instantaneously an infinite distance away? We've seen it happen in galaxies. Okay, so we can't find dark matter, dark energy, which is supposed to be 94% of the universe. And quantum electrodynamics, which most applications of it are accurate to 14 decimal places, is off 120 orders of magnitude on the cosmological constant. So it's out of these things that you start to question and you start to think differently. It's just a way to spark creativity, and there's books on sparking creativity.
Okay. I don't see any other new questions coming up. So, Dennis, I really wanted to thank you again for talking to our section. And I know, doing it virtually here in the fall, we hope to have more in-person type of discussions. And we will definitely kind of keep you in the loop. Hopefully you can join us as, AIAA that starts doing a little bit more in-person activities here in the fall. But thank you again for talking to us. And this video will